Thanks, Yoshua, and thanks for the organizers for having me here. So today I'm going to talk about work that our speech group is doing at Google, motivated towards, going end-to-end with speech recognition using deep learning. And before I begin, I'd just like to acknowledge my collaborators who have all contributed to this work: Andrew Sr., Oriel Vinyals, Hasim Sak, Ron Weiss, Kevin Wilson, and Yadid Hoshen. So before I begin, I just want to describe quickly the speech recognition problem, just to give a better background on where we're going to apply deep learning within this framework. So in speech recognition, you're given a sequence of acoustic observations O, and you want to find the best set of hypothesized words W. Now, using Bayes' rule, you can rewrite this as the probability of O given W, which we call the acoustic model, and the probability of W called the language model. Now, if we look at all sort of the subcomponents that go into, going from the raw signal all the way to a set of hypothesized words, we can break this into a set of subcomponents. So first, we take our raw signal, and we have a feature representation stage that we use to extract a meaningful set of features from our signal. I'll get into some of these details in the next slides. Then, given our signal representation, we then need to build a model to recognize some set of words or subword units. Now, we typically don't have enough data to build a model for every single word, so we build a model on some sort of subword units or states. And then we have a mapping that goes from states all the way to words. This is given by our decision trees in our lexicon. And then we have, a probability of a word should be followed by other words in the English language or in other languages, so that's given by our language model. So basically, what I want you to take away from this slide is that there's a whole series of complex building blocks to get from the raw signal all the way to a set of hypothesized words. And in the past, a lot of this has required, very speech-specific, domain-specific knowledge. And wouldn't it be nice if we could just improve and simplify parts of these pipelines, not requiring a lot of speech recognition knowledge, and do this within the context of neural networks? And that's really what this talk is about. So let's go through how we do feature extraction in a little bit more detail. So we first take our raw signal, and then we window this signal by roughly 25 millisecond windows with a 10 millisecond shift. We then take these windowed segments and we compute the FFT on each of these windowed segments. We then apply a log-mel filter bank, which mimics critical bands in the ear, and then we take the log of this to get a set of what we call log-mel time frequency features at every single frame, given by this sort of shown by this spectrogram over here. So you can see that this requires implementing FFT code. This requires having mel filter banks. And then wouldn't it be nice if we could just take the raw signal and pass it to the neural network and have it actually learn a good feature representation? So one thing I want to talk about is how can we replace this whole thing with the neural network, starting all the way from the raw waveform. Secondly, so once we have our feature representation, we then need to model a set of subword units. I'll get into what these subword units are on the next slide. But basically, the way we model these subword units is by a three-state left-to-right HMM, where the output distribution in each state is given by a deep neural network. Now, through time, we've seen a transformation on sort of what is the right acoustic model to use. So, 5 years ago, we were using Gaussian mixture models. And then around 2009, Geoff Hinton and his students showed very nice improvements with DNNs for a small phone recognition task. And then Microsoft came around 2 years later and showed about a 30% relative improvement with DNNs over GMMs on a conversational switchboard telephony task. 2 years later, in 2013, at IBM, we showed another 6% relative improvement over the DNN using convolutional networks. And then more recently, at Google, they've shown that using LSTMs gives really nice improvements over the DNN. So you can see there's all these modeling choices we have: DNNs, CNNs, and LSTMs. And I often get asked, well, what's the right architecture I should use for my problem? So another thing I want to address in this talk is sort of, what's a good architecture to use for speech? Maybe a combination of these makes most sense. So third, So what is the right subword units that we want to use for acoustic modeling? The easiest thing, simplest thing we'd like to do is to use phonemes. That's the smallest underlying unit which makes up a word. Now if we look at the phoneme ta in 4 different words, you can see that it's acoustic, or 5 different words. This is the spectrogram and time frequency representation. You can see that the acoustic realization of the phone ta is very different when surrounded by different left and right contexts. So really what we do is we, instead of making our subword units phones, we make it a phoneme surrounded by its left and right context, or what we call a context-dependent state, or a triphone. So if we have 41 phones, this means that the total number of context-dependent states is on the order of 200K, which is too large. We'll have data sparsity issues. So we have to use decision tree clustering mechanisms to cluster this down into a more reasonable number on the order of 2K to 10K, depending on the amount of training data we have. Now, wouldn't it be nice if we could model phones directly? We didn't have to go to context-dependent states. Another problem with using HMMs and context-dependent states is that during training we have to take an existing model and we have to align each one of our frames to the appropriate context-dependent state to do training. Wouldn't it be nice if we didn't have to do this alignment ahead of time? So these are sort of the 3 topics I want to talk about in this talk that our group is working on. So first is feature representation. Getting log model filter banks can be complex, and deep learning is very good at feature learning. So can we learn features directly from the raw signal? 2, in acoustic modeling, we've seen good results with DNNs, CNNs, and LSTMs individually. Is there an architecture that can combine these in a unified framework that makes more sense for speech? And 3, training requires an existing alignment. It requires context-dependent states. Wouldn't it be nice if we could just use phonemes and learn the alignment using something known as CTC? So first let me talk about how do we combine CNNs, DNNs, and LSTMs. So as I said a few slides ago, we've seen tremendous success with DNNs and speech recognition over the past few years. On the order of 30% relative. These are gains we rarely see in our field for acoustic modeling. And more recently, we've seen nice improvements with convolutional networks and also LSTMs. But CNNs, LSTMs, and DNNs are all individually limited in their modeling capabilities. So before I go into the architecture, I just want to define some basic notation. So let's say T will be our frame. X of t will be our input. This is a deep RNN. H of t is the hidden unit at every layer, and y of t will be our output. So Rez van Pasquinel, last year, he wrote a paper which discusses some of the limitations of RNNs and LSTMs, and we used this paper as motivation for coming up with an architecture to combine LSTMs with other things. So the first thing he says is that temporal modeling is always done on the input feature x of t. And if we were able to do higher level modeling on x of t, put it into a better space, then perhaps you would make it easier to learn the temporal structure. So we know that convolutional layers in speech are really good at reducing spectral variation in the input space. So we have 2 speakers speaking the same word with different vocal track lengths. They're really good at reducing that invariance in the frequency space and mapping this to a canonical speaker space. So what we'd like to look at is can we put convolutional layers before the LSTM? The second thing discussed in this paper is that the mapping between the last hidden unit, h of t, and the output is not deep. So there's no sort of nonlinear hidden layer. So he says that if you can reduce factors of variation in h of t, then you can easier predict the output. Now we know DNN layers are very good at sort of mapping the input into the DNN layer into a more discriminative separable space. So the idea is if we put DNN layers after the LSTM, will this better help us predict the output? So the architecture we want to look at is we first take our feature vector at a specific frame, x of t, our log-mel feature, and we pass this into the CNN to reduce spectral variations. We then pass this into the LSTM for temporal modeling, and take the output out of this, and pass this into the DNN to put this into a more separable space. And we'll call this combined CNN, LSTM, DNN architecture, CLDNN. And actually, if we look at sort of how speech recognition has been done historically in the past, while this architecture was motivated from, things that we had read in Razvan's paper, if we actually look at speech recognition in the past, for GMMs, we first started with a set of speaker-adapted features, and then we'd model these temporally with GMMs, and then we'd train these discriminatively using a discriminative objective function. And this recipe has been tried and tested for many large vocabulary tasks, and in this order has been shown to work well. So if you put the speaker adaptation after the discrimination, then you undo some of the speaker adaptation, for example. And if you look at the order of operations in this CLDNN, you can think of the speaker adaptation to be very similar to this. That's the CNNs are coming close to doing this. The LSTMs are doing the temporal modeling, and the DNNs are good for discrimination. So it's nice that this order is actually following an order that's been used in speech for a long time. Okay, so let's look at the CLDNN architecture. So the input into this, and all details of this can be found in my ICAS paper over here. But the input into this is a 40-dimensional log-mel feature, and then we have a frequency convolution layer, and the details of the sizes for the frequency convolution layer can be found in this paper here. But basically, it's an 8x1 filter in frequency and time. It has 256 outputs, and we pool by 3 without overlap. We then feed this into a linear low-rank layer that's just to reduce dimensions, and then we feed this into a few LSTM layers here. And the details of the LSTM can be found in Hashim's inner speech paper as well. The LSTM layer, we use 2 to 3 layers, 832 cells with a 512 projection layer, and we enroll this for 20 time steps. We then take the output of the LSTM and pass this into a DNN layer, use either 1 or 2 layers, and then follow this by linear low-rank layer. This is just to reduce dimensions before giving these to our outputs. So our initial experiments are on a 200-hour voice search task. And this model is trained using asynchronous SGD, and you can see a large number of context output targets, on the order of 13K. So the first thing we looked at is what happens if we put the CNN before the LSTM. Now, just as a reference, the LSTM baseline has a word error of 18.0. So we can see that this table here shows the word error rate as we increase the number of CNN layers. So we see first that we get improvements by adding CNN layers, but those improvements seem to stop after about 1. My guess is that it stops after about 1 because we don't pool in the second layer. We have not found it to be helpful. So most of the power in the CNN is coming in the first layer. But the takeaway from this is we see that if we reduce spectral variations with the CNN, then then it helps with better temporal modeling, and we get improvements in word error rate. Next, we looked at putting the DNN layers after the LSTM, and we see again we get improvements with DNN layers up till about 2, and then performance seems to saturate. So this shows us that if we create a more discriminative space with the DNN layers, then we can do better temporal modeling with the LSTM, and we can get improvements in word error rate. So now what happens when we combine them? So we see the LSTM is at 18.0, and by combining them, it seems to be complementary to put the CNN before and the DNN afterwards, so we can improve down to 17.3, which is about a 4% relative improvement in word error rate. So this 200-hour task that we looked at was just a very small task, small in speech terms, just to get a sense of if this thing would work. But really, we train a lot of our models on 2,000 hours. That's really where we want to test how robust this method is. We see lots of models that do well on small tasks, phone recognition tasks, but they don't carry over to LVCSR tasks. So we then went ahead and evaluated this on a larger 2,000-hour task, which is going to be a little bit noisier. And the models that are trained in this noisy test set are also evaluated in matched conditions on a 20-hour test set. So we wanted to understand, are we getting gains from CLDNNs because we're just increasing the number of layers? And if we just increase the number of layers in our LSTM, would we see similar improvements? So we do see, yes, as we increase the number of LSTM layers, this is the LSTM word error rate, we continue to get improvements, though it seems to saturate at 4. But if we increase the number of LSTM layers in the CLDNN, we also get improvements as well. We also looked at the effect of context. So when we train CNNs, we typically feed a feature with the surrounding left and right context as input. And we want to see, is the LSTM good enough to capture this temporal context, or do we need to give temporal context to the CNN? And you can see that there's actually no difference in performance giving just the input feature x of t or the temporal context. So the LSTM is good enough to model this temporal context. So that's nice because that simplifies the input feature into the CL-DNN. It's just a simple 40-dimensional log-mel feature. Okay, so to test the robustness of this model, we evaluated this on 4 different test sets, and I'll show you what these results are. So the final architecture we settled on, and this is mainly just to, to keep the parameters at some budget, was 1 convolutional layer, 3 LSTM layers, and 1 DNN layer. The first, and we evaluate our models after what's known as cross-entropy and sequence training. So after sequence training, it's the best. It typically gives us about another 10% improvement in word error rate, and this is sort of the best that our models can do. We typically deploy models after sequence training. So you see, if you compare the LSTM to the CL-DNN, this is a 16 kilohertz clean test set of 2,000 hours, and we report on clean. We see about a 5% relative improvement with the CL-DNN over the LSTM. If we look at a 16 kilohertz noisy test set, this is about average SNR of 20 dB, we see about a 4% relative improvement with the CL-DNN. Now if we look at an 8 kilohertz clean test set of 2,000 hours, we see about an 8% relative improvement over the LSTM. And if we look at an 8 kilohertz noisy test set, about a 7% relative improvement. So what you can see is that, across many different test sets on a large amount of training data, the CL-DNN seems to consistently outperform the LSTM. So just to conclude sort of the first part of my talk, I get asked many times, what's better, an LSTM or a DNN or a CNN? But I think in terms of speech recognition, it actually makes sense to combine them in a unified framework where the whole thing is trained jointly. And you can see by the improvements we're getting in word error rate. So now let me switch gears and talk about how we learn from the raw waveform. So to motivate that, let me just go back and refresh the standard way, the standard speech front end that's used. So we take our raw waveform, we then model this by a Hamming window, which is roughly 25 milliseconds, and we shift this every 10 milliseconds to have a set of windowed speech segments. We then take and compute the FFT on each of these, and then pass this through a MEL filter bank to mimic the critical bands of hearing, and do a log compression to have our log-MEL filter bank features at every frame. So what I want to look at is, can we replace this whole pipeline with the neural network? Can we start all the way from the raw waveform and go to context-dependent states? And is there benefit? We know that neural networks are good at feature learning. Is there actually benefit to learning this jointly with the rest of the network? Because log-MEL filter banks are sort of hand-designed, they're perceptually motivated. If you can design a set of filters that is, learned for the actual speech recognition objective at hand, is that actually better? So there's been a lot of work in looking at modeling the raw waveform. These are 4 papers that have looked at it recently. But none of those papers have shown improvements over just training a DNN with simple log-MEL features. And one of the reasons for this is that sounds which have similar perceptual and semantic identities can actually have different phase shifts, as I've shown here. So it's very important to model this. So when you see something like this, it seems like, doing some sort of time convolution and pooling would make a lot of sense to model these time variations. So if you look at how time filtering has been done to produce features in speech recognition in the past, one of the most popular approaches is to use gamma tone features. And gamma tone features perform very, very similar to log-MEL features. So let's look at how gamma tone features are created, because we took a lot of inspiration from that when designing our algorithm. So we first take a small window of our input signal. Let's say we'll call this M speech samples. You can assume M is about spans over 25 to 35 milliseconds, or to 16 kilohertz rate, it's about 400 to 560 samples. You then take P filters, and each filter is as an FIR filter of length n. Assume this is going to be 25 milliseconds, or about at 16 kilohertz. That's about 400 samples. And you're going to take each of these filters. You're going to convolve it against the input. After the convolution, you get n minus n plus 1. You then perform a half-wave rectification, and then you'd average to just get this down to one sample, and then you do some sort of compression like cube root or log, and then this would get you a frequency representation at a specific frame in time. This is typically how gamma tone is computed. Now you can see from all of these operations, convolution, rectification, averaging, compression, all of these operations can be done in a neural network. We can backpropagate through here to learn these filters. So the architecture we're going to propose is you take your window of speech of m samples. You have a set of filters that you're going to convolve against the input. These could be randomly initialized, or these could be initialized to be the gamma tone filters initially and then learned. I'll get into that in a minute. You take these and you convolve them against the input. That would again give you m minus n plus 1 samples. Half-wave rectification is a very similar operation to ReLU. So we'll proceed this by ReLU. And then we want to do some sort of averaging. Now we've experimented with LP pooling, max pooling, and average pooling, but max pooling seems to work the best, so we'll do a max pooling over here. And then we want to do some compression, and for us log seems to work the best. Now this gives us a set of frame level frequency features at a specific point in time, and we pass this to the CL-DNN. Now the whole thing is trained jointly, so we take the output targets, we backpropagate through the CL-DNN, and then backpropagate here to update these filters. So this operation, I should say, gives us one frame level feature vector. And then what we do is we shift our window along the input by 10 milliseconds to get another frame level feature vector, or to get another set of m samples which we compute features. So features are computed at every 10 milliseconds. So the raw CL-DNN architecture is, it's very similar to the CL-DNN, except now you're starting from the raw signal, and you have first a time convolution layer, and then the rest of this is just the standard CL-DNN that was shown in this ICAST paper. Also, I should mention the details of the raw convolution CL-DNN can be found in this upcoming interspeech paper. Now, the architecture for the CL-DNN is very similar to what I had shown previously, but the big thing is now this time convolution and the rest of this network is trained jointly. So we really are going from raw samples all the way to context-dependent states. So our initial experiments are on a 2,000-hour English voice search task, and it's the same setup as before. The logML system is trained with 40-dimensional logML features. The networks are trained with asynchronous SGD. And we have, again, a large number of context-dependent state output targets. So the first question is, what should we make the size of these filters? So experiment A right here is basically showing, here what we did is we made the time convolution filter span 25 milliseconds, and the input window also spanned 25 milliseconds, which basically means we actually don't do any pooling. And we compare this to when the input size is larger, 561 around 35 milliseconds, and we pool. Now both filters are initialized to be random for this experiment. And what you can see is you get a huge improvement in word error rate when you pool. And that's not surprising because, as I was showing before, we have a lot of variations due to phase shifts, and we need to reduce this. And without pooling, we don't reduce those variations. So pooling is very important, as you can see. So the next experiment we did is, we know that putting the lower layers of our network in a good space is important, right? So is it better to initialize these time convolution filters to be random or to be initialized with gamma tone? And that's experiment B here. And you can see that we get a small improvement, about 0.2, not much, but a small improvement, by initializing the filters to be gamma tone. And the third experiment we did is we said, well, let's just leave the lowest layer untrained. So that would effectively be a gamma tone feature. If we leave that lowest layer untrained, how does it compare to training the lowest layer? And you can see you get a small improvement by actually training the lowest layer versus keeping it untrained. So this sort of shows that it's important to learn features for the task at hand rather than having a fixed set of features created ahead of time. So now let's actually look at the features that come out of this time convolution layer. So this plot is taken after we've trained the whole network. We take one utterance. We take actually two different channels. You can see channel 0 and channel 1 here. These are 240-dimensional log-mal features. So this is the log-mal spectrogram, and this is the learn spectrogram. So what you can see is, the features seem to be very sensible. They seem, quite similar to this. They have a meaningful time frequency representation. So that's kind of neat. We just trained we trained from the raw waveform, and it seems that we do get a sensible feature representation coming out of this layer. So now the big question is, how does this compare to log-mal? So all of these experiments we did, we report with the same number of filters for log-mal and raw waveform, so 40. And we ran this on 3 different test sets, and we report after, to be complete after cross-entropy and sequence training. So the first is a clean 2,000-hour set. You can see that after sequence training, raw waveform is actually slightly better than log-mal. On a 20 dB noisy test set, raw waveform and log-mal match. And actually, on a slightly noisier test set with a little bit more reverberation in this set, the raw waveform actually does much better than log-mal. So now let's take a look at and try to understand why. So the first thing we did is we did a breakdown of word error rate as a function of signal-to-noise ratio, reverb time, and target-to-mic distance. What you can see is, and the red curve here is the raw waveform, and blue is log-mal. What you can see is that you get improvements with the raw waveform, small improvements at lower SNRs. But the real gains come when you have more reverberation and a larger target-to-mic distance. And so what we think is going on is these raw waveform filters are basically doing dereverberation. So when you have data sets, that have a lot of reverberation, these sorts of methods are helping more. Now, if we actually look at the learned filters, so what we did is we took the filters after training, we took the magnitude response of them, and we picked the center frequency, and we plotted this in terms of increasing center frequency. So this blue is log-mal, and the green is gamma tone. And these are 3 different raw waveform learned filters. What you can see is that the network is actually learning a set of auditory-like filter banks, and the bandwidth is increasing with the center frequency. What's very interesting is that the learned filters seem to give much more resolution to low frequencies. And this is another reason we actually think for lower SNR cases that the raw waveform is helping more. What's also interesting is that if you look at these 3 curves here, this is a raw waveform trained on noisy speech where you randomly initialize. And this is that same filter when it's initialized to be gamma tone. So you can see when you initialize to be gamma tone, we were getting improvements in word error rate. It also seems to give more filters put more filters in low frequency. So again, we can see another reason, putting more filters in low frequency seems to give improvements in word error rate. And then if you train on clean, you get even more filters in low frequency. So what you can see from here is that the filter bank is actually learning to adapt to the training data that it's trained on. Okay, we also wanted to explore, is there anything inherent in the CL-DNN architecture that we're looking at with the raw waveform that's helping, raw waveform and log-mal to match in performance? So we went ahead and started removing layers from the CL-DNN. So let's call CXLY-DZ a CL-DNN with X convolution, Y LSTM, and Z DNN layers. So we've seen this before. This is, the standard architecture we use, where both raw waveform and log-mal match at cross entropy, and the gamma tone initialization is better than the random initialization. Now, if we remove the convolution layer, which we do here, the first thing you can see is that, with removing the frequency convolution, the word error rates get slightly worse as opposed to having that in. But what's even more interesting is that there's no difference now between gamma tone initialization and random initialization when you don't have a convolution layer. Now, what we think is going on is that the frequency convolution layer is actually, because you're pooling in frequency, right? You actually require that the feature coming out of the time convolution layer has some sort of meaning, which is why it's important to initialize it with gamma tone. And if you remove that frequency convolution layer, you can see, the initialization doesn't matter. You don't really, you're not requiring as much meaning or ordering to the features as you do in the frequency convolution layers in there. So having that frequency convolution layer in there is actually important. So next we went ahead and started removing LSTM layers. So we went to 2, 1, and then a DNN. And here what you can see is that once we get down to 1 LSTM or no LSTM layers, the log-mel actually starts to do better than the raw waveform. So when we model from the raw waveform, there's temporal variations that we need to reduce. Now the time convolution layer is good at doing that on a short time scale. But the LSTM layers are good at sort of modeling temporal variations on a longer time scale. And we see that that's important in modeling the raw waveform. And when we start to remove those layers, the performance doesn't match. So sort of, just to summarize this section, using a CLDNN architecture, we're actually able to learn directly from the raw waveform and throw away this, FFT and log-mel computation. And you can see across 3 data sets, we're able to get the performance of log-mel to match raw waveform, and in some cases, a raw waveform does even better than log-mel. So the last item I want to talk about is CTC. So when we train our acoustic models, we need a set of labels and we need a set of labels for each frame and time when we do conventional training. So typically these units are going to be HMM states or CI phones. And there's 2 ways we can do the labeling. We can do what's known as a Viterbi alignment, where we assign hard labels. So we take an existing acoustic model and a set of labels, and at each frame in time, we assign a hard label to every frame to be one of these HMM context-dependent states. We can also use a soft assignment using the forward-backward algorithm, where you have a probability of having a specific label at every point in time. So, these existing conventional algorithms require having context-dependent states, and they require having an existing alignment. And we'd like to sort of remove both of those. So connectionist temporal classification is a sequence labeling technique that was introduced by Alex Graves around 2006. And he looked at this for handwriting recognition and for phone recognition. So in CTC, you want to take your input sequence, x1 to xt, and you want to align this with the target label sequence. We'll call this L. So CTC is not a conventional alignment because you introduce this additional notion of a blank label. So the idea is you align something at every frame, but if your model is not certain about outputting a label at a specific frame, or just it doesn't want to output a label at a specific frame, it's going to output blank. So the label assignment you get from CTC would look something like this. And then what you do is you collapse the repeats and you remove the blanks to get the actual label sequence here. So CTC is nice because you give it phonemes. You don't have to align it at every single frame, and it's going to learn this acoustic model jointly with the alignment. So let's see how this compares to cross entropy. In cross entropy, what we want to do is we want to maximize. In cross entropy, what we want to do is we're given a set of all our training data, which is a set of features and their corresponding label pairs. This is all the frames in that utterance T, and these are all the labels we could give. In cross entropy, what we want to do is we assume that the output of the neural network at a specific point in time is given by Y. We compute the cross entropy between that and the true label, where the true label is basically going to be a delta of 1 at the correct class and 0 everywhere else. And then if we take the gradient with respect to the softmax inputs, it's given by here. Now let's compare this to CTC. So we'll define Z of L as a lattice, which is all possible alignments of the input X with the label L. So our CTC loss across all utterances is going to be the log probability of the of P of Z given L, which is the probability for the correct labelings. Now we can compute this probability for the correct labelings given the forward-backward algorithm. And now the gradient you can see is going to be very different than cross entropy because it's going to be the output of the network Y minus the sum over all the correct labelings for the specific utterance. So if we look at, after we train a network with cross-entropy or CTC, we can see that, so this shows the posteriors, and you can see that this is a unidirectional LSTM and a bidirectional LSTM. And what you can see is that the posteriors, the model for cross-entropy training is always trying to assign a high posterior for one state at every single frame. Whereas if you compare this to CTC, these are the different labels. You can see that the posteriors are both unidirectional and bidirectional are very, very sharp. And most of the time the model doesn't care, it just outputs blank, which is these dashed gray lines here. Now, we compared this, we did experiments with CTC on, again, a 2,000-hour voice search set. This is an 8 kilohertz set. It's different than the test sets I was showing you before. And the models are trained with 40-dimensional log-mel features, and we actually explored just unidirectional, bidirectional LSTMs. And the cross-entropy models are trained with 13K output targets, and the CTC models have 41 phones. So this shows the word array. First, if you do cross-entropy training, fixed alignment with phone labels, you get a very high word array rate compared to if you use context-dependent states. Right? This shows the benefit of context-dependent states with cross-entropy training. But if you do CTC with just 41 phones, after sequence training, you can get very, very close to a context-dependent state model trained with 13K states. This is a unidirectional LSTM. And if you go to a bidirectional model, you can actually see now that CTC actually outperforms context-dependent states. So this is nice. With CTC, we can remove the complexity of both CD states and the need for an existing alignment. Okay, so just to wrap up, overall, I talked about sort of how can we remove a lot of assumptions and the complexity in the speech recognition pipeline with neural network-inspired models. So that includes, learning directly from the front end using raw waveforms, using an acoustic model that makes sense for speech, combining the benefits of convolution, LSTM, and DNNs, and then using CTC to remove CD states and alignments. And in the future, we'll actually look at combining raw waveforms CLDNNs with CTC. And sort of for the 3 topics, these are the papers that go along with the corresponding topics. So I'll take some questions.